equals 1,000. That's that can you see it mentality. 10 to what power equals 1,000? So we said, oh, well, x equals 3. And then we said, okay, 7 to what power equals 149? We said, okay, that's going to be -2 because of our negative exponents. So then we came to part C right here, and I left you off with a little bit of a cliffhanger. Dun, 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 right? And so we said, well, 1/2 to what power? So we just called it Z. 1/2 to what power equals -8? Now, I want us to kind of analytically think about this. Joey, what do you think? All right, so Joey says -3. So I'll start there. 1/2 to the -3rd power. And we want to say, is that right? Is that going to be -8? Now, I happen to know that 1/2 is what kind of number? It's a what? A positive number. It is a fraction, but it is a positive number. Good. Googly moogly. What do y'all want to bet? Who do we think this is? George. What do you think it's George? It's George. Guess who it would be. And they all guessed George. So you guys are correct. 1/2 is a positive number. And it's a fraction. When we raise a positive number to any power, I don't care if that power is positive, I don't care if that power is negative, I don't care if that power is 0. A positive number raised to an exponent is going to be what? It's going to be positive as well. And in fact, when I raise it to a negative exponent, that's as though saying, I just flip the fraction and change the sign of that exponent. And so that becomes a +8. So 1/2 to the -3rd would equal, good guess, Joey, but not quite there, would equal a +8. So if you considered what I just said, that a positive number like 1/2 raised to any number, it cannot equal a negative, right? It cannot equal, in this case, -8. So this is going to be an example where we say not possible or undefined, something like that. And that leads us to our first big point of the day, which I want you guys to all write down. You cannot take the logarithm of a negative number. Okay, I'll say that again. You cannot take the logarithm of a negative number. We need to discuss that question, why? Why is that the case? Why can I not take the log of a negative number? So let's slide over to our other page here. A little blank spot right here. And let's consider y equals b to the x. And perhaps we'll say that b is greater than 1. So what kind of exponential function is this? We said when the base is more than 1, it's what? Growth. So let's just say that this is exponential growth. Can you guys talk to me about the domain of that function? In other words, what all x values am I allowed to have? Jack? Okay, so what about these x values over here? Is the curve not over here? Which way is the curve pointing? Is it pointing infinitely to the left and infinitely to the right? Are there any holes? Are there any gaps? Are there any breaks or anything like that? No. So we could actually expand it to say all real numbers. So the domain here is all real numbers. Okay. I could pick a base that's greater than 1. So I pick a number greater than 1. 2. Okay, great. I can raise 2 to whatever power I daggone want. I can have 2 to the 5. I can have 2 to the 5 billion. I can have 2 to the -0.5. I can have 2 to the negative, 100. Well, I can have 2 to whatever power. I have 2 to the 0, 2 to the 1, 2 to the 3, 2 to the 4, 2 to the 5. So the domain here is all real numbers. That's what our curve kind of helps us see, is that Coach Morgan, that curve's going all the way to the left. And even though it starts going up real fast, it's still scooching out to the right further and further and further. So the domain of that curve is what, class? All real numbers. What about the range? The range is not all real numbers. What kind of y values do we see here? Alex? Yes, because the curve is above the x-axis. And we talked about, what's the A word, where the x-axis is sort of acting like a tractor beam. It's drawing it down, but it's never actually going to get there? Asymptote. Because this curve behaves asymptotically, it's never gonna get there. It's getting closer, but it will never get to y equals 0. We say greater than 0. So that's the domain, and that's the range. Well, friends, let me tell you, the inverse of this, y equals log base b of x, again, where b is greater than 1 here. You might not know what the graph of a log function looks like. So let me remind you that, well, actually, we'll have Jake remind us. Inverse functions, something happens with the domain and the range. Jake, how do I know the domain and the range of this green log function, given that it's the inverse of the orange function? Remember what we did with our domain and range?
No, I don't.
Okay. Nate? Very good. You swap them. The domain of my exponential function becomes the range of my inverse function. And consequently, class, the range of my exponential function becomes the domain of my log function. So whereas y was greater than 0, now x has to be greater than 0. And what does that mean that the graph is going to look like? Well, the graph is going to go infinitely up and infinitely down, hence the all real numbers on the range, and it's only going to be to the right side. Where the orange graph had a horizontal asymptote at the x-axis, this green graph has a vertical asymptote at the y-axis. They are inverses of one another, right? They were developed that way to like, I could say Mossy, plus and minus. I could say Alex, multiply, divide. I could say Will, square and square root. Now we've got a fourth pair of inverse ops. Raising a variable to the exponent or taking the log of some variable. Those are inverse ops as well. And because they're inverses, when we graph them, if I superimpose both graphs on the same plane, right? Here's the orange one. Here's the green one. And what line are they symmetrical about? Y equals x. Y equals x. So when we talked in section 10.1 and 10.2 about the inverse of a function, that's exactly what we meant. That the domain, very good, Nate, the domain and range switch. And hey, what about this? If I tell you that the point A comma B is on my orange function, Jack Candiato, what do you know is going to consequently be on the green function? Yeah, you said that hesitatingly. Don't hesitate. He who hesitates is lost. That's the law of the jungle, right? B comma A. All right. So these are inverse functions of one another. And therefore, now I want to focus back on this green picture right here. What did we say the domain was again? Greater than 0. That means that I cannot take the log of something that isn't greater than 0. You are not allowed to take the log of a negative number, in other words. Okay, you can't do it. Cannot take the log of a negative number. That's what we just said our big fat main point was. And here you see how this is doing just that. So that's a warning sign that at the very beginning I throw the brakes on and I say, hold on a second here. Don't go any further. We have violated the sort of the constitution, if you will, of this problem. No way this happens. Can't do it. Stop. Undefined. That's like taking the square root of a negative number. Very similarly, our square root function has a restricted domain, does it not? And so we therefore say, oh, you silly goose, you can't take the square root of a negative number. Okay. For that same reason, we throw the brakes on. We say you can't take the log of a negative number. Okay. Any questions on part C there? I know we spent a good amount of time talking about it, but we're laying out the groundwork for our log function. They're coming to get you, Lewis. Watch out. Nobody ever laughs at that joke. All right. Let's practice plugging in on a calculator. I know you guys might not have calculators, and that's fine. You don't have to. But I want to demonstrate, and in my demonstration, I'm going to ask a few questions. So let me get out ye old calculator. Here we go. Turn it on. Clear it out. Okay. So let's see, Andrew. Read for me what this is.
Natural number of 7.
Okay, good. So let's just call that the natural log of 7. Very good. And you answered actually my next question too. I was going to say, what is the implied base there? Class, what do we know as the natural number? E, Euler's number, about 2.71. Good. So there's an implied E as my base. So on the calculator, there's a button right next to the number 4 that says LN. That stands for natural log. And we talked about grammar and we talked about foreign language and why this reversal of the words. But the natural log of 7, that's all I've got to do. I just hit enter. And it tells me, oh, it's about 1.9. Okay. Now, how do you read, Luke, part B? What does this read? Very good. And so he's, again, answered my follow-up question. There's an implied base of what class? 10. So when we don't see a base, but we see Ln, it's an implied base of E, and we call that the natural log. When we don't see a base and it's an log, that's an implied base of 10, and we call that the what kind of log? A common log, because we got 10 fingers, and that's kind of a common thing. That's what we have as our base counting system. Now, right next to the number 7 on my calculator is the log button. And all I have to do is hit log of 35. And I hit enter, and there I go. I got my answer. Now, Ben, how do I pronounce part C? Beautiful, beautiful. That's not a natural log. That's not a common log. That's just a log, base 5 of 226. Now, my calculator does not have a nice fancy user interface. Some calculators do. Some calculators have it such that if you have a log whose base is not 10 and whose base is not E, and therefore you can't use those predetermined 2 buttons, you have another option, and it literally is real cute. It literally just puts a little blank square there for the base and a blank square there for the argument, and you can hit that button and then just arrow over to this blank, and you can type 5, and then you arrow over here to this argument. This blank, you can type 226 and hit enter. My oldie moldy calculator here on the screen doesn't have that luxury, and so I have to use what is called the change of base formula. Well, you remember talking about change of base formula? All right, so the change of base formula in this context is what I'm going to ask you guys to help me use. And shall we do it in terms of the natural log, or shall we do it in terms of the common log? Which one do y'all want? Because those are the 2 buttons my calculator has. Common log, okay. So we'll do it in terms of log base 10. All right. So we got the common log of something over the common log of something else. So George, which one goes on top? Which one's riding high on the hog? Which one's in the penthouse? Is it the 225 or the 5? I mean 226 or the 5? Okay, 5's down in the basement, baby. He's down in the dungeon. He's low rider. So we're gonna put him in the denominator actually. So positionally, you guys see how that 5 is lower? So he's gonna go in the denominator for my change of base formula. And then up here to 26. And that's all I got to do on my calculator here. So if I just hit log of 226 divided by log of 5, I hit enter, and I get my answers. Now, y'all told me to use the common log. Just as well, we could have done the natural log of 226 divided by the natural log of 5. As long as I keep the base the same on top and bottom, I'm straight. I'm going to get the same answer. You notice that, right? Look at the calculator. So the change of base formula is powerful in that It allows me to rewrite any given logarithm as I choose. I could pick a base of 10, I could pick a base of e, I could pick a base of whatever the heck I daggone want. Okay, as long as that base is greater than 0, not equal to 1. And where that comes into play is sometimes, okay, so a little sidebar example. It's going to be a challenge for you, okay? Sometimes what that looks like is I give you some information. Write the following problem down, okay? Log base 2 of 5 equals A. Log base 2 of 7 equals B. Log base 2 of 11 equals C. And I want you to find log base 11, 35 in terms of A, B, and C. Okay? Now, right now, you cannot do this problem. You don't know enough. I haven't taught you enough yet as far as our log properties. However, you could set this problem up. Consider what's given. What are the bases of all three of those given logarithms? 2. And yet down here, this has a base of 11. I need to change the base. If only, beard stroke, I had a formula that could help me change the base. Bum, bum, bum. Okay, so how would you, Drew, how would you express log base 11 of 35 in terms of our desired base 2? Rewrite that log, just like we did with George over there a second ago. Which one's going to go in the basement? So log base 2 of 11 is going to go in the basement. And what's going to go up top? Log base 2 of 35. Now are y'all already seeing something I could sub in? I could swap in? Which of those two logs could I substitute in place? Yeah, which one? The bottom one, yeah, I could. The denominator is the same thing as C. So I'm well on my way now to expressing this in terms of A, B, and C. Okay? There's a little trick you don't know yet. This is what I haven't taught you just yet. That log base 2 of 35 is the same thing as log base 2 of 5 times 7. And you got a log law that says if you got the log of a product, you can split that up as the sum of 2 logs. You haven't learned this property yet. I'm going to teach it to you today. And then all of a sudden, now what do you notice the numerator is? Substitution. What's the numerator the same thing as? A plus. Great. So this winds up equaling A plus B over C. Yay! Now y'all just did a hard algebra 2 problem. I kind of helped you a little bit, but that's all it takes. What got the ball rolling over here? How did we go from here to here? Change base formula. Somebody asked in the freshman class yesterday, it's like, where would I use the change of base formula at? And I'm like, you could use it in an exercise like this. And really, fellas, I mean, for Pete's sake, I could just plug in log base 11 to 35 on my calculator and get a numerical value for it. But as an exercise, we wanted to know what is it in terms of A, B, and C. And so what we're doing is we're training our brain to think in new ways. All right, so that's a really hard algebra 2 problem. That's an algebra 2 problem that I typically put on an algebra 2 test at the end of my chapter on logarithms. Okay, and it's not easy, but if you know change of base, and if you understand these properties that I'm about to teach you, you're going to be all right. Okay, now let's talk about a big, fat, hairy deal of a property. All right, let me zoom out enough. There we go. This is huge. All right, it's so huge, in fact, that we are going to scoot it down. I'm going to scoot this down. Now it's the only thing on the screen. Ooh, baby. This is called the inverse property of logarithms. And I've already taught it to you. You just don't know it yet. Okay, I snuck it in there on, through the back door. Robert Plant would say, I want to be your back door man. Y'all ever listen to Led Zeppelin? Well, I snuck this in the back door. You've already learned this. You just don't know it. The phrase that pays, can you see it, is the shortcut version of what we're looking at right here. Okay. Now, the main gist of this, I'll highlight for you. If you're going to write something down, I would write what's highlighted down. This is of the utmost importance as far as this screen is concerned. And what it pretty much says is that if I plug the exponential function into the log function, because they are inverses, that composite will simplify down to x, as we studied about in the, it says section 5.4. This was section 10. Let's see here, section 10.1. Okay. So if I plug the log function in to the exponential function, the same thing occurs. That composite, because they are inverses, that composite simplifies down to x. Now, what does that mean in practicality? That means that I can use the log as an operator to two sides of an equation to cancel out an exponential function and isolate the variable, the desired variable in the exponent. Or vice versa. Instead of taking the log of both sides of an equation, I could raise up both sides of an equation as a power. And as long as the base is the same, it'll work out. Let me show you what I'm talking about. Has everybody had a chance to write down what's in highlights? All right, let me show you what I'm talking about. Let's look at part A. I'm going to say, well, actually, this is easier. I'm starting off with an easy example. Oh my. All right, let's identify what's the understood base of that log that you see. You see log, you don't see a base. So what's it understood to be, class? 10. Okay, good. So it's an understood base of 10. Now I've got 10 to the power of log base 10. That's like saying plus 5. That's like saying times 2 divided by 2. That's like saying cube root. Those two functions undo each other. So what does this boil down to? It boils down to 56. Now you say, wait a minute, you haven't already taught me that. I sure have. I surely have. Set this equal to x and do the can you see it approach. It's in it's in exponential form. So if I were going to write it up a second way, I'd write it up in log form. So log base 10 of x equals log base 10 of 56. All right, what do you think that x equals, given that positionally speaking, log base 10 of x equals log base 10 of 56, you would therefore conclude what? That x equals 56. See, we've already done problems like this. The shortcut approach of can you see it, I kind of like a little bit better than the inverse property of logarithms. But the inverse property of logs says, well, just cancel those two out and you got 56. Okay, what about part B down here? E to the natural log of 6. What's the understood base of natural log? E. So those two cancel each other out. What does that first factor boil down to? 6. What does the second factor boil down to? 2. So this is just a simple 12. Very, very helpful property, the inverse property of logarithms. It allows us to use logs and exponents as inverse operators. Operator, can you help me place this call? Do-do-do-do. Anybody know that song? Yeah. Question, Quentin. So you said, I wrote my example instead of listening to yours. I'm sorry. You said 5 to the log base 5 of x. Oh, heck yeah. Yeah. When those two numbers are the same, they cancel each other out. Right? So very good question there, Quentin. The inverse property of logs is super duper useful. Now, look at this example right here. I got an equation that written up here. You cannot solve this equation by inspection. It's not like 2 to the x equals 8, where you just say, oh, well, x equals 3, Coach Walker. That's easy. Yeah, I don't know what number this is. 2 to what power equals 3? I don't know what number that is. It's an irrational, weird, funktastic number. Quentin, question. Okay? So I've taught you the quote, can you see it approach to this problem, right? Whereby you would tell me, whoops. You would tell me log base 2 of 3 equals x, right? Because we start with the base, we swoop around, log base 2 of 3 equals x. That's the way that I like working this problem. I taught you the can you see it approach. X equals this funktastic number, some irrational number. And oh, by the way, do you recall a logarithm is an exponent? Ooh, that's important. And what did we solve for? We said log is, what does the word is mean in math? Equals, and then guess what our exponent was? Our exponent was x. Okay, so log base 2. That's how I would work this problem. However, there's a second way of looking at it. Let's rewrite the problem in green now. 2 to the x equals 3. All right. Guess what I could do to both sides? There is an operator that I could do to both sides to get x by itself. Should I times by 5 to both sides? No, that wouldn't be helpful. Should I divide both sides by 8? No, that wouldn't be helpful. Although I could legitimately do those things. We've got the multiplicative property of equality. We've got additive. Ooh, what if I add 7 to both sides? Would that help? No, you silly goose, that wouldn't help. What if I take the log base 2 of both sides? In other words, what if I say, let's take the log of the left base 2, and let's consequently balance that out by taking log of the right, again, base 2. I choose base 2 because I'll do what I want, whatever. As long as I do it on the left side, I'll do it on the right side. But now, from our inverse property of logarithms, how does that left side simplify down? It just simplifies down to a good old-fashioned x, because those are inverse operators. That's like saying, ooh, there's a square root on the left side of my equation, so let me square both sides to get rid of that square root, to kill off that radical. And so now the left-hand side is just a simple x, and oh, look, there's the right-hand side is log base 2 of 3. I mean, we get the same answer. It's just 6 in one hand, half a dozen in the other. Some students prefer, when I teach them this, they're like, well, can you see it's stupid now, Coach? I like that way better. And you might feel that way too. That's fine. Okay? Being versatile is one of the jobs of a math student. Being able to work a problem in different ways through different viewpoints. Some of y'all might like the can you see it approach to solving an equation. Some of you might like the, hey, let me take the log of both sides. And that's fine too. All right, let's look at another example. I'm just kind of shooting from the hip here, making up some examples for you guys today. Let's do log, let's do the common log of x equals, now I don't want to make it that easy. Let's see. Let's do log base 3 of x equals 5. There we go, that'll be better. Log base 3 of x equals 5. Now, I don't know what the dump x would be in this case. This is not necessarily something I could compute in my head, right? How many of you guys want to do the can you see it approach? Anybody like the can you see it approach? I hate you all. Okay. Thank you, Charlie. Charlie's got my back. All right, Charlie, if I do the can you see it approach, what do I do? Where do I start? Pardon? I couldn't hear. At 3, good. So we start with 3, we swoop around, can you see it? So 3 to the 5 equals x. 3 to the 5 equals x. And I don't know what 3 to the 5th is, but that's our answer. We got x by itself. Now, for my money, I think that's pretty daggum simple. But do you know what you could do as an alternative? Instead of doing the can you see it approach, here we go, log base 3 of x equals 5. You could operate upon each side. Do I want to add 1 to both sides? No, that's not going to help. Do I want to take the square root of both sides? No, I could do that if I wanted to, but it's not really going to help. What I could do in this case, I'm not going to take the log of both sides since there's already a logarithm there. I could exponentiate both sides. I could raise both sides up, make them an exponent. And what base do you think I ought to pick? I ought to pick a base of 3 because when the bases match up, those are inverse operators and they cancel each other out. So check this out. Here's what we'll do. We'll make log base 3 of x the power that we raise 3 to on the left. We'll make 5 the power that we raise 3 to on the right. In other words, I have performed the same operation on both sides, kept it balanced. We exponentiated the left side. We exponentiated the right side. Both bases were the same, so everything's gravy. Now what do you do on the left-hand side? Cancel both of those functions out. Because the base is the same, per our inverse property of logarithms, which we said was oh so important, both of those have simplified down, and I've got a nice, neat x equals 3 to the 5th. Did somebody say something? Question? No? All right. Now, look, fellas, for my daggone money, I've got the red way all day, every day. Me and Chuck just rolling down the road, doing our can you see it approach. There's nothing wrong with the blue approach. Just sometimes it takes a little bit longer. All right. Now, that being said, our time is up. Let me encourage you, on your Delta math, there are 15 questions, very easy questions. Some of you might have already gotten them done. If you have not, log on and do it. And in the meantime, have a wonderful weekend. Live Jesus in our hearts. Awesome. Thank you, guys. Y'all have a great day.
You know when our finals will be?
Yes, I do. I'm sorry I haven't emailed parents. I'll tell you the date right now. It's going to be Monday, I'm going to guess and say 17. Let me pull my